every scientific instrument confirms the IPV was out of contact for only a fraction of a second. Isn't that correct, Doctor?
A fraction of a second Earth time, yes.
Earth time?
Senator, I believe that the machine opened up a wormhole. A tunnel through the fabric of space-time, also known as an Einstein-Rosen bridge. Now, because of the effects of general relativity, what I experienced is approximately 18 hours passed instantaneously on Earth.
Doctor, isn't it true that these wormholes you speak of are merely theoretical predictions? There is no evidence they actually exist, is there?
There's no direct evidence, no.
Tell me something, Doctor. Why do you think these aliens would go to all this trouble, bring you tens of thousands of light years, and then just send you home without a single shred of proof?
They said that's how it's been done for billions of years.
That's very neat, Doctor. You have no proof, because they didn't want you to have any. A phenomenon known in psychiatric circles, I believe, as a self-reinforcing delusion.
Is that what you think, that I was delusional?
Well, I do think you may have suffered some kind of an episode, yes. I do. Doctor, are you familiar with the scientific precept known as Occam's razor?
Yes. It means that all things being equal, the simplest explanation tends to be the right one.
Exactly. Now, you tell me, what is more likely here? That a message from aliens results in a magical machine that whisks you away to the center of the galaxy to go windsurfing with dear old Dad, and then a split second later returns you home without a single shred of proof?
You really gonna sit there and tell us we should just take this all on faith?
Please answer the question, Doctor.
Is it possible that it didn't happen? Yes. As a scientist, I must concede that. I must volunteer that.
Wait a minute, let me get this straight. You admit that you have absolutely no physical evidence to back up your story.
Yes.
You admit that you very well may have hallucinated this whole thing.
Yes.
You admit that if you were in our position, you would respond with exactly the same degree of incredulity and skepticism.
Yes.
Then why don't you simply withdraw your testimony and concede that this journey to the center of the galaxy, in fact, never took place?
Because I can't. I had an experience. I can't prove it. I can't even explain it. But everything that I know as a human being, everything that I am tells me that it was real. I was given something wonderful, something that changed me forever. A vision of the universe that tells us undeniably how tiny and insignificant and how rare and precious we all are. A vision that tells us that we belong to something that is greater than ourselves, that we are not, that none of us are alone. I wish I could share that. I wish that everyone, if even for one moment, could feel that awe and humility and hope. But that continues to be my wish.
And Professor, you were saying there might be another way to avoid the grandmother problem. I threw up the multiverse idea, or the new universe idea, I guess, instantly when you pervert what was supposed to happen. What other way might there be?
Well, it's the boring way.
There's a boring way?
Yeah, as they say, they call it in Star Trek a causality loop. I like that. It's better than the way the physicists call it. But basically, it's that every time you go back in time, you just repeat the same future, sort of like Groundhog Day. And you just repeat. You can go back in time, but you have to repeat exactly the same events the second time around. And then it's sort of not like it's not very much fun.
But
I mean, those are the only two solutions of that grandmother paradox that I know of. That, of course, the great thing about nature is if there is time travel, if it is possible, and we don't know, and that doesn't mean it is possible. It may be impossible. What it really means is we don't know.
Okay, I'm still not grasping though. You said you would endlessly be repeating that action.
Yeah.
How would that work with respect to the linear time that's going on in the world and the events that are going on in the world?
Well, it just means time would be circular instead of linear.
Circular. It would become circular only for you, or it would become circular for all?
For presumably for all.
Oh my God! You mean so one person going back and blowing it in time could put the whole world in this circular, repetitive, and never-ending loop?
At least, yeah. Well, at least the world is that person's experience.
Oh my!
It would mean that nature itself, because remember, space and time are both dynamical in general relativity, and so you can go through a circle in space, and in principle, you might imagine you go through a circle in time. But if space-time is circular, then it's a property of space-time, and so it allows time travel, but it doesn't. But it's very specific about how it allows it. So,
well, they do say history repeats itself, right? So maybe somebody already blew it for us.
Exactly, maybe.
But that's a kind of a pathetic ending for the world, isn't it?
It's sort of not what you'd like with time travel.
Yeah, that's right.
And as I was about to say, that if time travel is possible, the real solution to the grandmother paradox is probably something we haven't thought of at all. And that's what I always find fascinating about nature, is it tends to surprise us. And so, if I had to bet, I'm betting time travel isn't possible, because it just seems so difficult to imagine resolving this issue, and I'm talking about it in principle. I mean, even if it were possible in principle, I have to say that we know that we've already been able to calculate how much energy would be required to make a wormhole or do that kind of thing if it were possible.
Yeah.
And even if it were possible, the energy required would be so immense it would be more than the mass of our galaxy. And so we're talking hypothetical here. And that's what people should realize. I always worry when one talks about this that people think that, and NASA, spending money trying to build warp drives, but it's kind of a waste of money at this, because we're talking issues that are hypothetical right now, not things that you can have an engineer, sort of develop a new kind of box to do right now. And so these are fascinating questions, I happen to think, and I hope your listeners do. But they're issues that involve questions of principle that are not right now or in the foreseeable future practical.
What would be required would be an unimaginable new power source. But don't we have a habit of running into these unimaginable new power sources?
Well, we do have a habit of being surprised. We have a habit of running into new things in the universe, that's right. It would have to be an unimaginable new power source of it, but not just of regular power, of a kind of energy that is different than any kind of energy that we see anywhere in the universe, except in one place.
Yes, but if you go back to the early days of dynamite, let's say, that in actual years, it wouldn't be that long ago, right? And you were to demonstrate nuclear power to those folks, it would be unimaginable. It would be magic.
Absolutely.
It would be alien, perhaps.
Oh, absolutely.
To them, as unimaginable as this new power source we're speculating about.
Yeah, that's true, and so that doesn't mean such things can't exist. However, it is important to realize that we have, with our telescopes and other apparatus that we have in our laboratories, been able to explore the universe, in fact, observe the universe on out to distances of billions of light years away.
Yes.
And the amazing thing that we happen to have discovered is that the laws of physics are the same everywhere. And we understand how stars work. And so if there were incredible new power sources, we should be able to see them, if you wish. And the nice thing about the universe is it's big and it's old. So no matter how crazy something is, if it's not impossible, it happens all the time.
Right. How does this let's slide right in to the question of whether there's probably life out there or not. Statistically, with what we know about the known universe and the physics of everything, you said appears to be the same. wouldn't that make it pretty, in fact, more likely than not, when you crunch the numbers, that there is going to be life out there, almost definitely, in fact?
Well, I don't know whether almost definitely is but I'd say if you asked me, I'd bet that there's life out there, yes. I would say, given the fact that we know from our own experience that all you need to have life is water, solar power, and organic materials. I mean, on Earth, life originated about as soon as the laws of physics would have allowed it to. Within 100 million years of the time the Earth cooled down enough to be stable for organic reactions to occur, life formed. And so it seems to be fairly ubiquitous on Earth, and therefore, and one of the things we do know about space is that all of those things exist. We know there's lots of water, we know there's lots of starlight, and we even know there's lots of organic materials. One of the things we learned from the Hale-Bopp comet was not that there was a spacecraft behind it, but rather, when we looked at the spectrum of it, it actually had complex organic materials, the basis of amino acids. And so all of those things exist throughout space. And so I have a hard time believing there isn't life elsewhere in the universe. Now, the question is there intelligent life? That's a much more difficult question because we don't know that intelligence is an evolutionary imperative. I mean, we're here by a series of sort of cosmic accidents. An asteroid that just killed the dinosaurs 65 million years ago made room for mammals, and we happen to be mammals. Now, maybe that there are other ways to intelligence. We don't know how it works, so it could be that there's lots of life in the universe, but hardly any of it is intelligent.
Maybe the dinosaurs weren't just given a long enough run.
Exactly, that's true. We don't know. It could have been that if they had been, they'd be watching I Love Lucy now. But we don't know, and so I'm willing to believe, even if intelligence, however, is very, very rare, that there's still intelligent civilizations out there. I think that's not unlikely. What, however, is extremely unlikely, in fact, so unlikely as to be virtually impossible to imagine, is that those intelligent civilizations are coming here right now, or have in the time we've been cognizant.
Why is that hard to imagine?
Well, there's lots of reasons, but let's work through them.
Sure.
First of all, as I've tried to explain earlier, to go at anywhere near the speed of light requires an incredible amount of energy. Okay, so you'd have to basically harness the power of a star to take a spacecraft that would, take people or any beings that are sort of our size and move them from one place to another at near the speed of light. Now, that's not impossible. You could imagine some civilization that's incredibly advanced could harness the power of a star and do that.
Well, let's think about that for a second. In other words, is that likely that there would be such a civilization, such an advanced civilization? The Big Bang occurred, 15 billion or so years ago?
Exactly.
Now, that's a lot of time. Relative to that 15 billion year mark, there's a lot of material way the hell out there that's been around for a lot longer than we have.
Exactly. Our sun is only 5 billion years old. So we're newcomers.
So there would have been lots of time for...
Yes. You also have to ask the question, and we're a good test. We're the only test case we have. Do intelligent civilizations survive for billions of years? And that's and you talk about your Geiger counters, the other things. You got to ask the question: do intelligent civilizations kill themselves off before they ever get to the point of being able to do that?
Yeah.
A lot of people think that's quite likely.
More than likely.
But maybe they do, and maybe there are intelligent civilizations that have been around for billions of years and are presumably, therefore, incredibly advanced. But even if they could harness the power of a star, it would be hard to imagine why they would do that, take all of that incredible energy and resources that would be required. I mean, whether it's money or whatever else, fuel is money. The incredible resources it would take to basically demolish a star and use it for space travel, to come all the way here just to do kinky experiments on psychiatric patients of some Harvard psychiatrists. It just hardly seems an appropriate use of resources.
Have you had any good heart-to-hearts with Dr. Mack? Have you?
Very brief ones. I've talked to people who more than Dr. Mack, with people who have either claimed to have seen UFOs or been abducted. Uh-huh. And I think the point is that, and this is hard to say and hard to explain appropriately. It's not that I can say that those things are impossible or they didn't happen, because God knows I wasn't there.
You're an astronomer and a theoretical physicist as well. It seems to me appropriate to ask you about this. Lately, the new theory is that not only is the Big Bang, did the Big Bang occur, but everything is now beginning to actually accelerate away from everything else, so that in the end, it's going to be kind of a thing where I actually read a story where the light from distant stars will begin to blink out. The night sky will begin to save that which is really close to us. The night sky will begin to be devoid of stars. Everything will move away from everything else until we finally freeze to death in the darkness.
Yeah, I think I wrote that.
You wrote that? That was you that wrote that, huh? That's pretty graphic stuff, Professor.
Yeah, it's the future. Well, it is indeed one of the biggest surprises in the last century that when we look out, it looks like the expansion of the universe is indeed accelerating, which is crazy. It's insane, right? Because gravity, as I said before, is supposed to be attractive. It's supposed to slow down that expansion.
Right.
But there does seem, on a large enough scale, to be some kind of cosmic anti-gravity, something that's causing the universe to accelerate. And we know what kind of stuff will do that. It's crazy. If you give empty space energy, if you associate with energy with empty space, and by empty space I mean nothing, no particles, no nothing, nada, but empty space, if you give it energy,
yes,
then that energy, according to general relativity, is gravitationally repulsive. And it will cause the universe to accelerate. In fact, Einstein postulated such stuff early on when he called it his biggest blunder. He invented something he called the cosmological constant, because originally when he developed general relativity, we didn't know the universe was expanding at that time in 1916, and his theory was the same as Newton's theory. Gravity sucked. It said that you couldn't have stuff just sitting out there. Gravity would be universally attractive, and therefore everything would collapse together. And in his universe at the time, it looked like the universe was just sitting out there. And so he said, well, let's add a little repulsive force, give empty space this kind of energy, and it'll balance on large enough scales the gravitational attraction of distant stars and galaxies, and everything will just sit there. And then we discovered the universe was expanding, and you didn't need that extra force, because if the universe is expanding, well, gravity can be universally attractive and simply slow the expansion. So Einstein said, gee, I wish I hadn't invented that thing, was my biggest blunder. Well, his biggest blunder may have been saying he was blundering, because, in fact, it looks like, what we're seeing today is it looks like the universe really has exactly the kind of stuff that Einstein first postulated, and we don't understand what it could be or how it got there. And, in fact, we don't understand anything about it. It's the biggest mystery in physics and astronomy, and that is incredibly exciting. I mean, because, again, what people seem to think of as scientists like to understand things. Actually, scientists like to not understand things because it gives us something to do.
Yeah, yeah.
And this is the biggest mystery in nature.
So it means there's a force out there throwing everything apart that we don't even begin to understand, put succinctly.
You got it. It involves very little energy. Let me point that out. I mean, even though it's making the whole universe expand, the density of energy that would be required to make that happen is so small that it would not be noticeable on Earth. Okay, I mean, empty space would have an energy which is like the equivalent of a mass of 10 to the minus 30 grams per cubic centimeter in energy, and that's very small. That's the equivalent of having one proton per every cubic meter of material. It's almost nothing. So on our scale, it's not noticeable, which is why it escaped our notice for so long. But when you build it up on large enough scales, there's lots of empty space out there, then it begins to have an effect. And the effect is, but there's one thing that you said, lest your listeners get too depressed. If the universe is indeed accelerating, it is true that stars and galaxies that are far away from us now will be eventually moving away from us faster than the speed of light.
Yes.
Because that's allowed, by the way, in general relativity.
And so when that begins to occur, we can't see it anymore.
We won't be able to see them. That's absolutely right. But the stars in our galaxy will never do that. I mean, until they burn out.
Well, I know, but that's going to be relatively close by. All that nice full sky that we get now, the Milky Way and all the rest of it.
Exactly. I mean, so the stars in our night sky are not moving away from us. They're trapped in our galaxy. But, of course, the point is they're going to burn out anyway, so the sky will get dark in our galaxy because the stars will burn out. But it is really amazing that in a period, in a cosmic sense, and people like me who worry about cosmic time have thought a lot about this. In fact, I've written scientific papers on this, that in a relatively short time frame, in the period of 10 to 100 billion years, which may sound like it's, not worth thinking about, but in fact, stars will still be burning, astronomers could still be around, civilizations much like our own could still be around 10 to 100 billion years from now because there'll be stars just like our sun burning.
Pretty optimistic.
Yeah, but, well, maybe it's optimistic. But in that time frame, in 100 billion years, most of the rest of the universe will disappear. And, in fact, the longer we look, we used to think the longer we look, the more we'd see. We now know in 100 billion years from now, astronomers will sort of be out of business in the sense that they won't be able to see anything outside of our own galaxy. That's the bad news. The good news is, of course, I've tried to argue to Congress that we should fund astronomy now while we have a chance to do it.
Using that argument, huh?
It doesn't work, of course, because for a congressperson, the long-term future is 2 years.
Yeah, I know. I know. Well, all right. There's a rumor going around, and there are people going around saying that there is a planet out there just beyond what we can generally see, which they're calling this mysterious planet X. And it's supposed to be some large planet or perhaps a dying sun, which some believe comes swinging by Earth every now and then, causing varying degrees of trouble depending on how close it gets. But actually, there have been stories, ABC ran one, that they did indeed spot something out there that does kind of look like a dwarf, burned-out sun or something or another. You know anything about that?
Well, I've heard rumors about various things. I do know that in fact, I mean, there can be lots of, I mean, as you probably know, what we define by a planet is changing all the time. Some people like to call Pluto a planet. Some people in New York City, for example, they don't call Pluto a planet anymore at the planetarium there, much to the chagrin of people. There are lots of objects farther and farther out.
Do you think they have any right to strip Pluto of its planetary status?
No, I don't think so.
It seems raw to me.
Yeah, I'm totally against it.
Okay.
I like Pluto, in fact.
Yeah, I do too.
And but there are lots of other objects out there further than Pluto in our solar system, and what you call planets, and what you know, if they're smaller than Pluto, are they a planet? So and as our telescopes become more sensitive, we can find dimmer and dimmer objects. But a star has a lot of mass and has a lot, and whether it's faint or not, it produces a significant gravitational effect, and therefore nearby in our solar system there are no other stars, because the gravitational effect would be just huge. Now we are detecting farther away. We are beginning to be able to detect objects that are very dim. That may be failed stars, but they're not. Yes. They're not going to affect they're not affecting the dynamics of our solar system.
Well, let me ask you this: is there such a thing as a rogue planet or a rogue star? In other words, something that is traveling independent of other immediate objects that it's been affected by?
Well, in a sense, yes, we all are. I mean, in our galaxy, this is another thing that's kind of interesting for people to realize, is that we're moving relative to background stars, because we're all moving around the galaxy, but we're moving independent of each other. So in fact, stars that are nearby us now will in 100 million years be on the other side of the galaxy. So we're moving apart from other solar systems, and there are stars that are moving close to us, and there are stars that are moving far away.
Yes, but a fairly close call has fairly profound.
Oh, absolutely.
Right.
Absolutely. If a star approached, if another stellar system approached, even 50 times the size of our solar system, it could perturb the dynamics of our solar system and kick out some planets. And people have done calculations of what would happen if a stellar encounter occurred. And of course, what generally happens is things get kicked out, and planets get thrown out, and orbits that are now stable become unstable.
Yeah, very, very profound effect. So would we see this coming, or could it come to be a surprise for astronomers? Are we watching the relative velocity, or relative to us, of everything out there, so that we're so sure this wouldn't surprise us one day?
Well, with stars, it's not a worry. I mean, at least in a cosmic time, we don't have to worry. But smaller objects, we certainly have to worry about. There are 1,000 objects, small. I'm talking about asteroid-sized objects, 10 kilometers and larger, that are known to exist in that are on potential Earth-crossing orbits, and we, with absolute certainty, we can say that we're going to be hit at some point in the future, because on average, an asteroid that's 10 kilometers or larger hits the Earth about once every 100 million years. And the last big one we know of was about 65 million years ago. So depending upon whether you're a betting man or not.
Well, but suppose there were something as large as a planet. And we haven't seen it all yet. So
yes, but we can in fact, but we know for certain that in the region within the distance of Neptune to us, okay, there are no other planets, okay?
Yes.
And no other objects as massive as Pluto or larger. And what's amazing is with our telescopes we can actually see objects that are much, much smaller than Pluto, as I say, asteroid-like objects that are extremely distant, and therefore it's hard to imagine that something with the mass of a planet that's close enough to have impact upon us in a kind of century time scale or two would have escaped our notice. But there are many objects that might have, I mean, just a 10-kilometer size object is pretty bad.
What about something with a return time of, say, 3,600 years? I mean, that is possible, isn't it?
Well, it would be possible, except if it were massive enough to have to impact upon us in 3,600 years. The last cycle around, it would have been massive enough to cause to dramatically perturb the Earth's orbit.
Oh, yes,
and we know that it didn't because of the fact that life and many other forms of many other tests we can do tell us that the climate on the Earth has changed, but not that radically.
Well, yes, but what I'm saying is perhaps this 3,600 years, it would be a bit closer than it was last 3,600 years. That would change, would it not, to some degree, past to pass?
Yeah, I mean, it's not impossible.
Yes.
It's highly unlikely, but it's not impossible.
I see.
It's because, I mean, you have to have it change dramatically from one over to the next, and you could always imagine things get perturbed by something else, and that you don't know about, and their orbit changes dramatically, and suddenly they come a lot closer, and I mean, so it's impossible to rule such things out. It's highly unlikely. It's much more likely that we'll get zapped by something smaller, which would still be pretty darn bad.
Oh, I mean, sure. Something the size of what happened to the dinosaurs would do nicely. Yeah. I'm sure. Are we prepared to stop something like that now if we saw it coming?
That's an interesting question.
Yes,
I mean, there have been those movies, and if we had, it's not impossible for me to imagine that we would be able to do something if we had enough lead time, because you need 10 years lead time probably.
Like what?
How to stop it?
Yes.
Well, I don't think Hollywood got it that wrong. I mean, if you have enough lead time, you could imagine having a spacecraft have an encounter with the object and do one of many things. Either of course, have nuclear explosions and somehow break it up, or perhaps that slowly divert its trajectory just enough so that it misses the Earth. But you need a lot of lead time, and 6 months ain't going to do. And that's why it's important, and by the way, we are doing it, to have a network of telescopes looking for such a thing.
Indeed, yes, but more times than not, Professor, I read the news stories here on the air, so I know. The news stories read, yesterday, Earth had a close encounter. Or they read, last week, astronomers now tell us Earth had a very close encounter. And so, you're saying if we had 10 years, a lot of times we don't even know we've had a close encounter until after.
No, I think what the news stories say is that yesterday someone discovered an object that might have a close encounter with us.
Uh-huh.
And by close encounter means pretty far away, by the way. The good news is that we're a pretty small target in a pretty big space, and that's why these things on average don't happen very often, fortunately for life on Earth. And what is true is that we already have found 1,000 objects that we can monitor and know their trajectories. And with a good deep space telescope network, we could probably pretty effectively monitor almost everything that is likely to impact upon us in 10 years.
Well, how come mostly amateurs discover all this?
Well, the nice thing about it is it takes patience, but it doesn't take huge telescopes. You don't need the Keck telescope to do this.
Yeah, I know, but by the time you're the size for Frank's telescope, you don't have 10 years.
Well, you actually, for most of these objects, you probably do. But what you only have 10 years if you get all of them. That's the point. For any given object, it's unlikely it will hit us within 10 years. But if you want to be certain that you're safe and that you're not missing anything, you have to scan the whole sky, and that's what an amateur can't do, because you have to have a network that constantly scans the whole sky, and therefore you have to have a coordinated network of lots of amateurs, if you wish, or a bunch of professionals. And so people have said we should have a coordinated deep space network, and it's not that expensive, and it's happening, and I think it's obviously useful that it happened. But the good news is the likelihood is extremely, extremely small, because the average impact time is 100 million years, and that means in any given century, you got a chance of 1 in a million of getting hit.
Huh.
And so, that's pretty good odds.
Those are good odds for us, but cosmically they're pretty bad odds. And
they're pretty bad in the sense that we will definitely be hit in the future. And it's, there's going to be a lot of things in the future that are going to be challenges for life. And an impact by a comet or an asteroid is certainly one of the long-term potential disasters. There are a lot more if you actually think about it. In one of my books, I sort of start thinking about all those things, and it's kind of amazing we're still around with all the different disasters that are going to happen. If we escape that one, and if you're willing to wait, just a mere 2 billion years, then we're in for a much worse experience, because the sun will be 15% hotter, and we will experience a runaway greenhouse effect and look like Venus and have a temperature of 1,000 degrees.
Oh.
Unless, of course, we can figure some way out of that.
That'll definitely produce changes. What are the most likely scenarios, Professor, for man doing himself in, aside, and I mean by that, I guess, man doing himself in, or the extinction? No, I don't mean that. I mean the extinction of man, whether by his own hand or by another hand, a hammer from space, whatever. We've already talked about it. What are the most likely scenarios?
Well, I think it's hard to imagine. In order to completely get rid of, life is very robust, and that's one thing people should realize, is that in the history of the Earth there have been many mass extinctions, but none of them, as far as we know, have ever extinguished all life on Earth. It's amazing when you look at there have been times where there have been dramatic overhauls, but even there, some life forms have survived. So it's very robust. And now of course, there are a lot of life forms that are more robust than us, like cockroaches.
Yeah, I've been asking about us, though.
Yeah, us. So it's hard. What I was going to say is, it's hard for me to imagine anything that we would do that would completely exterminate us as a species. I can imagine getting rid of a civilization, but some humans would exist. But so I think the things that are likely to exterminate us as a species are likely cosmic in origin. And they're the one we've talked about. I think the most likely significant event will be, in fact, an impact from a large meteor asteroid.
Okay.
That would, and if one that was size 10 kilometers or so, maybe 100 kilometers across, if a 100-kilometer across meteorite hit the Earth, it would essentially evaporate all of the oceans, and it's hard to imagine much life surviving after that.
All right, now let's look at our own hand. We are deep into the human genome now. We're modifying. I heard the other day we actually created a virus for the first time. We actually created a virus. And, of course, people in the war labs are working on, viruses to vector things that, if somebody went oops and it got out, it could go raging around the world like a wildfire, just extinguishing life everywhere it went, and it would go everywhere.
Over 2 years after the coronavirus was first detected in China, I remember that, and after at least 6.3 million deaths have been counted worldwide from the pandemic, the World Health Organization is recommending in its strongest terms yet that a deeper probe is required into whether a lab accident may be to blame. What do you think when you hear the word probe? Grow up, then.
Well, one could imagine biological accidents that do huge damage.
Yes.
But again, if you look at any past examples of such things, they usually don't completely eradicate things. The plague killed many people in Europe, but there were people who were immune to it, and because there are mutations, and so you're right. I think biological damage is a huge threat.
That was Mother Nature, though. If man puts his hand in and actually designs something to be aggressive enough and deadly enough to do the job, Mother Nature leaves a little hole in there. but gee, we're getting pretty bright.
Yeah, we are, and I think we are likely to certainly create great changes. I like to be more optimistic, and I think that we will essentially redefine what we mean by life over the next century. We will, as we understand the genome, be able to, and by the way, at the same time as our computer technology enhances, my expectation is that we will be able to create life where it didn't exist before, and we'll be able to change what we mean by life. And a lot of people find that terrifying, but I think it's inevitable. And you're right. In the process, we might destroy it as well. I think, as I said, if anything, we've learned that life is incredibly robust. It's been around continuously for 4.5 billion years. Not quite 4.5 billion, 4 billion years on the Earth, in spite of lots of disasters, and biological ones included. And so I'm less pessimistic about that, but I am certainly prepared to recognize that what we now think of as our present life form, and what we now think of, we tend to think of ourselves at the top of the evolutionary ladder.
Yes.
But of course, that's not true at all. We're just a branch, and what's next will affect it ourselves. And I actually expect, when I think of the science fiction future, that we will combine self-aware computers with biology to make new life forms.
Didn't we just, I think it was IBM that succeeded in teleporting a bit of light from here to there?
Uh-huh.
So then, did they really do that?
Well, yes.
They did.
Well, yes, they did. I mean, they picked a good word, right? Because, when you talk about a transporter or teleportation, everyone gets excited. And what they did is an interesting application of the laws of quantum mechanics to destroy a single elementary particle, in this case a photon, a piece of light,
right,
in one place, and instantaneously produce the exact same configuration somewhere else.
Boy, that sounds just like Star Trek.
It does, doesn't it?
Yeah, it does.
The problem, there are lots of problems with that, however. First of all, it was a single piece of light, not a human being or a bowl of oatmeal. And in fact, the reason they were able to do that is they exploited the laws of quantum mechanics, which apply on elementary particle scales, and in this case, they used the fact that this particle was very carefully created and monitored and controlled throughout the experiment as an individual particle, so that it didn't interact with other particles, et cetera, et cetera, et cetera. Well, unfortunately, of course, we are not so carefully prepared, and things at macroscopic scales, human scales, are not carefully prepared quantum mechanical configurations. The particles in our body are colliding against other particles every second, and with the air, and all sorts of stuff. So all of the weird aspects of quantum mechanics that were exploited in that experiment, which are...
Well, I understand that if you were to transport a human being with that technology, you'd be jelly on the other end.
Well, you wouldn't be able to,
even that might
you wouldn't be able to do it. The point is,
right.
You wouldn't, because you are exploiting at that scale phenomena that we can't experience at human scale.
Indeed so. But my question is that not perhaps the first step that will result one day, long from now, perhaps, though in teleportation for real?
I would argue
no.
And the reason is that the quantum mechanics is the weirdest thing. It's weirder than anything we've talked about. It's so weird, even if we know the mathematics of it, you can never truly understand it, because it's just particles behave so crazily on ultra small scales that everything you think is sensible goes out the window. For example, a baseball. I throw a baseball to you. If you're in the at the other end of a baseball field, well, of course it follows some trajectory from me to you,
yes,
right? You told us what the trajectory is.
Correct. Yes.
An electron that goes from one place to another.
Yes.
Well, you can show that in no sense does it follow any. If you don't measure it in between, if you just measure it where it started and where it ended, there's no sense in which it followed a single trajectory from one place to another.
Huh.
In fact, it traveled on many trajectories at the same time. That's insane, but it's true. Like it or not, that's the way the world behaves on small scales. Now, we can exploit that craziness, and that's exactly what this kind of experiment was doing, was exploiting that quantum mechanical craziness. But you can only exploit it on the scale where quantum mechanics where quantum mechanical phenomena are manifest, which is either very small scales or particles or configurations that are isolated from every other Because the minute you tap a particle, the minute you observe it or the minute you affect it, you screw up all that quantum mechanical phenomena. It just goes out the window. And so in order to have that neat thing, that teleportation, you have to have something that's completely isolated and completely controlled. And therefore, I think the likelihood of transporting humans that way is the same as the likelihood of humans being able to walk through walls.
Yeah, but you know, a quantum computer might straighten all that out.
A quantum computer, by the way, this might help us make a quantum computer. A quantum computer is basically a computer that does many, many calculations at the same time.
Right.
And that's exactly what elementary particles allow you to do, because remember, they take many paths at the same time. So that is realistic, or at least you could imagine it. I don't really, I think there's been a lot of hype, but I think it's worth working on. That is realistic, but I think the idea of a transporter is electrons, by the way, tunnel through. That's something else particles do. If I take a ball and I throw it at a wall, it does one of two things. It bounces off.
Is it possible, Professor, that a quantum computer would lead us toward, if not movement between dimensions, at least perhaps communication or the extraction of information from other dimensions?
Well, first of all, other dimensions would have to exist, and we have no evidence that they do.
Well, you suggested the possibility.
Well, that one of the things that physicists are considering is the possibility there are extra dimensions. It's an interesting idea, but I do want to stress that we have no evidence whatsoever that they exist. But the quantum computer would operate in our universe using our laws of physics, and therefore one of the aspects of quantum mechanics is, as weird as it is, it never takes you out of your own reality, okay? And so there's limits to the weirdness of quantum mechanics as we understand it and as we can test it. And so a quantum computer would allow us to do many things in the sense of potentially, well, unfortunately, it would allow us to break codes, and that means that a lot of the codes that store money in banks and other things would be breakable, and we'd have to figure out new ways of keeping information safe. But it's not likely it certainly wouldn't be able to obviate the laws of physics as we know them.
All right. A lot of people want to talk to you. Much as I would like to continue, I've got to go to the phones a little bit here. On the international line, you're on the air with Professor Lawrence Krauss. Where are you calling from, please?
I'm calling from London in the UK. My name's Jeff. I called before.
Okay, Jeff, welcome.
Okay, thank you. I had some questions for Professor Krauss.
Yes.
Sure.
Okay, first of all, the idea of life transporting around, not so much intergalactically, but within our galactic, has actually been proposed by Marshall T. Savage. He reckons it could be done with about 1,000 years. Well, maybe yes, maybe no, but I certainly believe that we could travel to somewhere like Alpha Centauri fairly quickly, because it would only take us about a year to reach light speed if we accelerated at 1G.
If you accelerate continuously at 1G, it would take a year, a year or two to reach light speed. That's a true statement.
Right, and
but of course you have to have the fuel that would continue to do it. That's the problem.
Well, now Alpha Centauri, though. I see the fuel problem again. Yes.
The fuel problem. I mean, you still got to have something that's accelerating you at 1G continuously for a year. Try it.
Yeah, but that makes an assumption that you're going to be accelerating something the mass of something like a space shuttle. But what if you could reduce the mass and inertia that was required?
Oh, absolutely. There's no doubt that the only sensible way to imagine sending things outside of our solar system to explore beyond it, it seems to me, especially if you want to do it in a reasonable time, is to have micro objects. To imagine intelligent chips that are minuscule in size, because when it comes to interstellar travel, mass is the villain.
Nanotechnology, then.
Nanotechnology is the only sensible way to consider doing that. I agree with you there completely.
And the other one was teleportation. Now, I always heard that maybe the biggest problem with teleportation, apart from the amount of energy, was that the breaching of Heisenberg's uncertainty theory. But I'm not so sure that would happen, provided that you didn't actually extract the information of either location or direction of the things that are being teleported.
Well, in fact, you are correct in the sense it's not that they get around for your listeners, by the way, Heisenberg uncertainty principle says I can never know where an atom is and what it's doing at the same time, basically. Mm-hmm. I can know one or the other exactly, but I can never know both exactly, and you'd kind of think if I want to reproduce something, I would have to know both exactly, right, at the atomic level. But in fact, these kind of teleportation experiments get around that by actually never measuring the configuration that they're trying to reproduce. At any point in the process, they never actually make a measurement, and therefore they never the laws of nature allow it to be reconfigured exactly without you ever having had to measure it in the process. It seems like again a swindle, but it's a swindle that works. So I agree that does not make teleportation of individual quantum states impossible, because we've been able to do it. But unfortunately, all of my problems with transporting human-sized objects continue to be exist.
I agree with you. I mean, it is very, very difficult to imagine it scaled up to human size. But
or anything beyond a very carefully prepared quantum mechanical system, which is generally of order atomic size.
Sure. Thanks so much. And I have read your book. It's a very good book.
Thank you.
Okay, take care. Speaking of books, you've written quite a few. Let's see. Atom, a single oxygen atom's journey from the Big Bang to life on Earth and beyond. That would be your latest, or your...
That's my latest.
Your latest,
book,
okay.
Yes.
And before that, Beyond Star Trek, Physics from Alien Invasions to the End of Time. Boy, you're good with titles. The Physics of Star Trek. So you were a Trekkie, huh?
Well, I never dressed up, but I certainly watched it.
Quintessence, The Mystery of the Missing Mass. The Fifth Essence, The Search for Dark Matter in the Universe. And Fear of Physics, A Guide for the Perplexed. Very interesting. Star Trek was more than just another television show, wasn't it? I mean, somebody obviously had an awful lot of insight into... They must have had a theoretical physicist on staff someplace or another.
You'd think so, but they really didn't. I mean, Gene Roddenberry used to know a little bit, and they used to go talk to people at JPL every now and then. But and some of the people I've talked to, some of the writers, some of the art directors, like to read Scientific American. It's kind of amazing how often they kind of their intuition was very close to the real world, even when I think they really didn't know what they were doing. It's kind of amazing. One of my favorite examples is an early episode of Star Trek. I think the third episode, they go too close to the gravitational field of something that they call a black star, and they get sent back in time. Right?
Yes. Oh, yes.
And I remember looking at that and saying, well, that's okay. The writers didn't know the word is black hole, but they came pretty close. And then I checked the air date of the episode, and it aired about 6 months before the physicist John Wheeler invented the term black hole.
Isn't that interesting?
So, they almost invented the term. It's kind of...
What about the replicator?
Well, the replicator is a version of the transporter that just works on omelets and that sort of thing. And it takes. See, the idea is if I'm going to transport you, at some point I have to have your entire pattern stored in a computer, right? So I can recreate you at the other end.
That's right. Hopefully accurately.
Yeah, exactly. So why bother? So the replicator just sort of gets rid of the middleman. If I can, take your pattern, I might as well just store a pattern and use some atoms from something else to recreate it, and I can make a cup of coffee or an omelet.
There's something to think about. All right. Breakfast. I interview a very interesting man like yourself named Dr. Michio Kaku. I'm sure you know him.
Yeah, I know him.
I'm sure you know him. And he maintains that, when you really press him to the wall, I mean, everybody tries to be an optimist, but he maintains when you press him to the wall that the odds of mankind surviving the discovery of element 92 and then on from there, are really terrible. What do you think?
Well, I think in order to imagine surviving and maintaining the kind of society we live in for any length of time is going to require a kind of concerted organization that I've never seen in human history before. I mean, we can't even get our act together, and in response to global warming, we have an administration that can't even look beyond the next few years, and as a civilization, we're going to have to deal with, in 100 years, a loss of fossil fuels, and so it's hard to. I hope that humanity will be able to coordinate itself, but it's easy to imagine many ways that it won't. And so, yeah, it's easy to be pessimistic.
All right. Back to the lines. Wildcard line. Hello, you're on the air with Professor Krauss.
Yes.
Where are you? Where are you?
Carson City.
Okay.
It's the capital of your state.
Yes, sir.
I had a question about the theory of relativity.
Okay.
Now, everybody, when they explain it as the ship leaving the Earth.
Uh-huh.
And when it goes away, time slows down for the ship.
Uh-huh.
What about when what about when the ship returns? Will time then speed up again?
Well, it's a very good question. In fact, what I'm going to tell you is even more strange. Okay, so be prepared. So when the ship's moving away, you look at it, and indeed it looks like that clock is slowing down compared to you. But you know, if you're sitting on the ship and you're looking back at the Earth, guess what you see? It looks like the clock on the Earth is traveling slow compared to your clock. It's completely reciprocal. So you might say, well, if that's the case, how can anyone age faster or slower than anyone else? It turns out that when the ship is traveling in one direction, it's completely reciprocal. When it's traveling back, it's again completely reciprocal. But it turns out all of the aging happens when it turns around. So, you know, it is absolutely true that if you traveled out at near the speed of light for 100 years and then came back for 100 years, the person on the ground would have aged 200 years,
but all the
you
aging...
wouldn't have aged hardly at all.
Yeah, but you just said the aging occurs as you're turning around. Why? Why?
Well, you have to take my physics class for me to tell you that. It's just it's a little complicated to explain in the radio. But it turns out that the actual here's the way to sort of understand it. Galileo and Einstein told us that two objects moving relative to one another, you can never prove who's moving and who's standing still, right? If you've ever been on a train on a train track and you look at the one nearby, you know, sometimes you don't know when you're in a subway train whether you're moving or it's the one on the other side, right?
Right, of course.
And it's absolutely true. The laws of physics tell us you cannot prove that you're absolutely standing still and someone else is moving. You're just moving relative to one another.
Right.
Well, so the two observers are exactly identical as long as they're moving in uniform velocity. But the time when they become different is when the other observer slows down and turns around. Because when you slow down, you experience a force, G-forces. You get pushed up against the steering wheel or you get pushed back into your seat when you speed up. And that's when you are different than the person on the ground. And that's, therefore, the time when all of the action happens. So that's what separates the two observers, is one had to slow down and speed back up again in order to make the round trip.
That's incredible.